Good morning, or should I say good day, or should I say good evening, wherever you are. Good day, welcome to my video. Now, in this video, we are most definitely looking onto organic chemistry, which is the second year module for chemical engineering students. So in this module, we are most definitely going to focus on some of the basics before we can do some problem solving questions. So here we are going to learn everything about organic compounds, okay? So now what you see here on the picture, it is father of organic chemistry, Frederick Waller. He is the first scientist basically to synthesize an organic compound using inorganic compound in laboratory. The first compound that he once synthesized was urea. Okay, he's the first scientist to synthesize urea using silver cyanide in the lab. Back then, scientists used to believe that the organic compounds are only found naturally. You see, the thing is, that's a truth. That was truth back then because that's what all scientists used to believe, right? But he came along, this guy, and he said, no, 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 no. The organic compounds can also be synthesized in the lab. Now, this is one of the reasons. Today we have multiples of organic compounds. This is one of the reasons why do we have multiple organic compounds. It's because of one of the properties of carbon, okay? The organic compounds are most definitely composed with carbon. So one of the reasons is that carbon can bond 4 times, okay? So for a fact that carbon can bond many times, that simply or shows that we have multiple of organic compounds today, okay? So kudos to this guy, and may his soul continue to rest in peace, the father of organic chemistry. Right. So now we're going to start with section number 1, whereby we are most definitely going to learn the structural, the bonding, and the molecular properties of organic molecules. Think of organic compound. An organic compound, you're going to learn everything about it. You're going to learn about the structures. How do they actually look like? How do we represent them? We're going to talk about the bonding. I mean, like, for example, a structure of organic molecule, it has the atoms in it. We're going to learn the bondings of the atoms. We're going to learn the bondings between the compounds or between the molecules. And we are also going to learn about their properties of these organic molecules, okay? Like I said, there are many of them, okay? Right, so now most definitely, before we can start with everything, let us just introduce the organic chemistry. What is this organic chemistry? It's simply the study of compounds of carbon, which is, I mean, like, not every compound that has carbon, it is regarded to be organic compound. These are organic compounds, okay? Organic chemistry, it is the study of organic compounds. So in this case, organic compounds, they are most definitely composed of carbon, but I was saying not every compound that has carbon, it is regarded to be organic compound. It depends, and you will see most of organic compounds, they have carbon, hydrogen, some they have carbon, hydrogen, sulfur, some they have nitrogen, some they have oxygen, some they have halogens, which are group 7 elements. But you will see as time goes by, when we talk about the organic compound, what type of compound are we actually referring to? Like, for example, carbon dioxide, CO2, carbon dioxide, it's a compound, but not organic compound, okay? It is inorganic compound, okay? But then let us continue with the session. Now, when you talk about the compounds of carbon, which are organic compounds, like I said at the beginning of the video, we have the naturally occurring compounds, and these naturally occurring compound, they are composed with carbon. And these examples of naturally occurring compounds are DNA, proteins, and carbohydrates. These compounds that I have just mentioned, DNA, proteins, and carbohydrates, these are the examples of organic compounds, okay? And these examples of organic compounds, we can find them naturally. Like, for example, living organisms, they have what we call the DNA in their nucleus of their cells, right? So not only the nucleus, even in out of this, but the thing is, the living organisms, they have what you call the DNA, and the DNA compound or molecule, it is the organic molecule or compound, okay? The proteins, our bodies forms proteins such as keratin for our nails, you understand what I'm saying? Hemoglobin for our blood, pigmentations and all of those things, the carbohydrates, some of these compounds, we consume them from other living organisms, okay? So these are organic compounds which are naturally occurring. Like I said, after the study of Friedrich Holle, as scientists, as chemists, now we know that the organic compounds are not only occurring naturally. We can synthesize organic compounds in laboratory. So that means another compounds of carbon, we say they are synthetic compounds, such as what? Such as drugs and pesticides, okay? For an example, we know the drugs, we know the morphine. Morphine is a type of a drug but this drug, okay? It's a type of a drug that is used to relieve a severe pain. And another type of a drug, we have a guanine. Guanine is for anti-malaria or anti-malaria, okay? It's a drug that can be synthesized in lab. Pesticides to control, I mean, like farmers, they know they use pesticides a lot, right? These are organic compounds. These are examples of organic compounds, but these are from the laboratory. These were manufactured by man-made. Okay, they were made. These are man-made organic compounds. All right. So now let's have a quick review on chemistry basis of what you need to understand before we can do complex stuff. Okay. So let's learn about the Lewis structures. Okay, what are Lewis structures? Okay, let's talk everything about Lewis structures. Remember, we're going to talk about the compounds, the organic compounds, but yet you have to know how do we structurally represent these organic compounds, okay? So now the Lewis structure of these organic compounds, we say they show the two-dimensional connections of atom, which is true, right? So now I'm just going to talk about methane, okay? It's a chemical formula or molecular formula of methane. But the moment, say for an example, C, it bonds with hydrogen, it bonds with hydrogen, it bonds with hydrogen, it bonds with hydrogen. We can represent, once more again, we can represent this compound like this using the dots, okay? Using the dots, we know that using the dots, can use dot and crosses, it's fine, but I'm just preferring to use the dots, okay? We have hydrogen over here, hydrogen over there, hydrogen over there, hydrogen over there. So this is a Lewis dot structure, and this is also the very same as Lewis structure, just that here we use the bond lines, okay? This one bond line, it represents 2 electrons shared between the 2 atoms, okay? So now we say this is a 2D shape, it's not 3-dimensional shape, okay? This is a 2D shape. So we say it shows the connections of atoms. We can see that carbon and hydrogen together, they are bonded by these this one pair of electrons, okay? Right, again, Lewis structure, they show valence electrons only. Now, this is what is happening. Carbon, from our periodic table, carbon it is in group number 4. That means it has 4 valence electrons. So in this Lewis structure, you do not see, you are not seeing other atoms. Remember, the atomic number of carbon, it's 6. But here, you only see 4 electrons of carbon because it is in group number 4. So meaning Lewis structure, it only shows the valence electrons only. Even for hydrogen, we know that hydrogen has 1, okay? But then this 1 electron from hydrogen, this 1 electron from carbon, remember these 2 guys over here, they're gonna do some contributions, and amongst these 2 electrons, they're gonna share them together based on their contributions, okay? So these are the valence electrons, and therefore bonds, 2 shared electrons are shown as lines. Now, like I said, these 2 presentations of this organic compound, it is the same, but here we see the bond lines, okay? So for a fact that you see the bond lines, this one bond line, like I said, they represent two shared electrons. And therefore we have the non-bonding electrons, we call them the lone pairs, are shown as dots. Now, say for an example, let's talk about ammonia, okay? Let me draw, okay, I understand, okay, but it's fine. Ammonia is just a compound, but it's fine. I just want to show you something when we talk about, even here, well, okay, you can even look, but I didn't want to come here, but it's fine. This compound over here, we have the structures, I mean, we have the bond lines to show the structure of this. We have the bond lines, and then we have the pairs of electrons that are not bonded. These pairs of electrons, we call them the lone pairs, okay? All right, and therefore, we have two things to consider when talking about the Lewis structure. You cannot just draw a Lewis structure without considering these two things, okay? We're going to talk about the octet rule under the Lewis structure, and we are also going to talk about the formal charge under the Lewis structure. Now, let's firstly discuss the octet rule. There is a lot going on over here. So now, two things to consider, which is number one, octet rule. From the periodic table, the second row elements such as boron, carbon, nitrogen, oxygen, and fluorine, they want to form bonds such that they acquire 8 shared electrons, okay? We say these atoms, they obey an octet rule. An octet rule states that these atoms, when they are stable and when they are bonded with other atoms, they're supposed to be surrounded by 8 electrons. Now let's go to this structure. We have carbon, right? Which is one of the atom that is found in the second row element. So now this carbon, it is surrounded by how many electrons? Remember, the valence electrons at the beginning was supposed to be 4. But because this carbon, it is now stable because it has bonded with 4 hydrogen atoms. Therefore, this carbon is surrounded by 8 electrons. We have 2, 4, 6, and 8. So that means this carbon within this molecule, it has obeyed an octet rule. It is surrounded by 8 electrons, okay? But you'll see when it comes to boron, it will see, but we'll discuss that. Now, hydrogen only wants two valence electrons. We know that hydrogen only wants 2 valence electrons, not more than that, okay? Because its atomic number is 1. So its outer energy level will be filled by only 2 electrons, okay? And therefore, first and second row elements from the periodic table can sometimes, you know, that the first and second row elements, we know we have the hydrogen, the helium, we have through the lithium, it's, what is it? Beryllium, yeah, I think it's beryllium, and so forth. So now, these elements in these rows can sometimes have fewer than 8 valence electrons, but never more. They can never be more than 8 electrons. Okay, so that's just how it is. For an example, you can have a look at lithium. Okay, it's one of the examples. And therefore, third row elements and the lower elements below third row elements, we say the d orbitals allow for more than 8 electrons, which is, we know that, right, from the material science. We have learned all of these orbitals, right? We have learned that we have the s orbital, which has a number of orbitals, which is 1, and the number of electrons supposed to be 2. And we have learned the p orbitals, the d orbitals, and the f orbitals, right? We know that the d orbitals, the number of orbitals, there are 5, right? 1, 2, 3, 4, 5. I don't know if you still remember that. Think of an Aufbau diagram, okay? Think of an Aufbau diagram. So we have 5 number of orbitals for d orbitals, and then we have 10 number of electrons in the orbitals, okay? So that means, hence why we're saying the third row elements, they have d orbitals, which allow for more than 8, because d orbital, literally, it can take maximum number of 10 electrons, which is most definitely more than 8 electrons, okay? All right, so now as we continue with our lesson, this is what This it's what we call the electron configuration, okay? But this electron configuration, it's electron configuration of carbon atom, okay? Now, what you see here on this electron configuration, you can see that when you add these numbers together, these exponents together, you're gonna get 6, right? So this 6, it represents the atomic number of carbon, because atomic number of carbon, it's 6. So meaning we have 6 number of electrons, 6 number of protons, okay? Right. So now this is what is happening here. We have the s orbital. Remember, the s orbital can take a maximum of 2 electrons. And therefore, we have the p orbital. It is the p orbital, right? The p orbital can take how many number of electrons? I mean, remember, the p orbital says I can take 6 number of electrons, right? So how many number of orbitals are there? There's supposed to be 3. Okay, all right. So now, on this electron configuration, we call them the core electrons, and they have lower energy. And then here we call them the valence electrons. I want to show you something. Let me draw something. Let me clear this thing first, okay? I want to show you something. I want to show you the atomic model of the very same atom, which is carbon, right? So now say here we have the nucleus. We know that the nucleus have protons and we know that nucleus have protons and neutrons. Now, surrounding the nucleus of the atom, we have the orbitals, right? Say, obvious, for carbon, you're going to have 2 orbitals, okay? We're going to have 2 orbitals. This is the atomic model of carbon, okay? Now, this is what is happening based on this atomic model. How many number of electrons of carbon do we have? I said there are 6. So remember, the first energy level will take a maximum of 2 electrons, right? Will take a maximum of 2 electrons. And therefore, how many number of electrons from 6 now are left? For carbon, we have 4. So that means the remaining 4 will come here, because the second energy level can take a maximum of 8 electrons, so that when you add them together with this, they become 10, which is p orbital. So that means here we're going to have the remaining 4 electrons, because this can take a maximum of 8 electrons, right? So we have 1, 2, 3, 4, 5, 6 electrons. Now, this is what is happening. From the electron configuration, this and this, they represent the same thing, just that presentation is not the same. This is the atomic model, and this is electron configuration. So this s orbital, it has 2 number of electrons, which is the core electrons are lower. This is the core, and this is the outer energy level for carbon. So we have 2 electrons, and then we have 4 valence electrons on the outer energy level. Do you understand what I'm saying? So these are the valence electrons. So that's why we are saying on the Lewis structure, we use what? We use the valence electrons. We represent our compounds with valence electrons when they bond with another compounds. Okay, so that means carbon. This is the atomic structure of carbon. And therefore, this is an example of hydrogen. We know that hydrogen, its atomic number is 1. That means it has only 1 valence electron, okay? So this can obey an octet rule, basically, because it has only 1. So if the first energy level is filled, therefore, that means hydrogen will be stable. Remember, this is the first energy level. This is the second energy level. In this case, for carbon, first energy level, it is fully occupied. That means outer energy level, it is not occupied, meaning this carbon, it is not stable. It needs to react with other atoms where they're going to share the electrons. And therefore, there will be 8 electrons on this energy level. Therefore, we can say now carbon, it is stable. Okay. Again, here we have an example of formaldehyde. This is a type of organic compound. We're not going to talk more about it, but I'll just say this organic compound. It's from this functional group that we call aldehyde, since well, there's a carbonyl, but we'll discuss that later on. So formaldehyde, It's one of the examples of organic compound. So what you see here on this formaldehyde is that all of these atoms are stable, like carbon and oxygen. They have obeyed an octet rule. That means this atom, it is surrounded by 8 electrons. This is surrounded by 8 electrons. But do not forget that hydrogen can never obey an octet rule. Okay. All right. So another type of organic compound that we can talk about is borane. This is called the borane, or you can call it the boron hydride. Okay, so this borane, like I said, I understand here we say that the second row element wants to form bonds such that they acquire 8 shared valence electrons. But this molecule, I am happy to tell you that this molecule, it is not stable at all. Okay, it is even regarded as Lewis acid. This is an unstable molecule. Okay, and it is super highly reactive molecule. Do you understand what I'm saying? But it is unstable simply because it did not obey an octet rule. Because if you have a look at this B, we know that boron, it is in group number 3 from the periodic table. So that means the valence electrons for boron, it's 3. So meaning these hydrogens, as they react with this boron, what is going to happen? We're going to have the shared electrons, right? And therefore this boron is going to be surrounded by how many number of electrons? Remember, one line represents 2 electrons, meaning we're going to have 2, 4, and 6. So boron, it is surrounded by 6 electrons. It is not surrounded by 8 electrons. That means boron, it is an exception to reach to obey an octet rule, but at the same time, this is a compound which is unstable, but yet it is reactive, highly reactive. Okay, so we say B can react with lone pairs, and so I am saying to you to get an octet rule. So boron can obey an octet rule, but in this case it is unstable, but it has formed a compound. In this case, once more again, this boron can obey an octet rule when it reacts with lone pairs. In that case, we are talking about the Lewis acid. Okay, and then again, it can also dimerize too. So for a fact that it can dimerize, that means boron can react with boron. That's what it means when you say it can dimerize. It can react with itself. It can react with the similar molecule of it. You understand what I'm saying? All right. Now, another thing that we need to consider under the Lewis structure is that we have the formal charges, okay? So when we talk about the formal charges, we are talking about the electron ownership, okay? We are not talking about the actual charge that this molecule or this atom is positively or negatively charged. No, that's not what we are basically talking about. Okay, so again, the formal charges, it is determined by assigning the electrons to specific atom as a bookkeeping device. Okay, now I'm gonna jump from here to here so that everything can make sense to you. Okay, what is actually a formal charge? Now here we have a compound, right? It is CH3 plus ion. I mean, like, we know that methane, it's CH4, right? But what you see over here, it is CH3 plus, sorry, plus ion. Okay? I'm sorry about that. So now, this is what is happening. Here we have a compound, right? But say, for example, we want to know the formal charge on carbon of this compound. Now, what you see over here, it's 4 minus 3, which is equals to 1. But you want to ask yourself, why did I use 4 minus 3? Maybe some will say the valence electrons for carbon is 4, and then we have 3 hydrogen atoms. Therefore, their valence electrons is 1, 1, 1. That means it's going to be 4 minus 3. Oh, okay. But the thing is, when you get to other molecules, it's going to be difficult for you to say that, and it wouldn't make sense. Now, there is a formula that we can use to determine the formal charge. Now, the formula that we can use to determine the formal charge, it is called Fc is equals to valence electrons subtract bonds plus dots, okay? We can use this formula. This is bonds, B, okay? Bonds, the bonding. So that means to determine this, we can use this, okay? So now we have the molecule over here, right? And we want to determine the formal charge on carbon. So how are we going to do that? Now we're going to say the formal charge on carbon. Remember, we are talking about carbon. The formal charge on carbon is equals to the valence electrons of carbon. It's 4, right? Because it is in group number 4. Subtract how many bonds are there on carbon. We go to carbon. We have 1, 2, 3. We have 3 bonds on carbon plus dots. Do we have dots around the carbon? No. So that means our dots over here is going to be 0. And therefore, 4, here we're going to have 4 minus 3 plus 0 is most definitely 3. And therefore, we have 4 minus 3, which is equals to positive 1. So that means the formal charge of carbon in this molecule, it is most definitely going to be positive 1. Right? Right. Now say we have a complex molecule like this one. Okay? Say we have a complex molecule like this one. So we want to determine the formal charge on each atom, in each central atom, okay? So we have carbon, right? So if we want to determine the formal charge on carbon, what are we going to do? Okay, formal charge once more, again on carbon for this molecule. Remember, this is the formula that you're going to use. Formal charge is equals to valence electrons, subtract bonds plus dots, right? Plus dots. So now, what is the formal charge on carbon in this molecule? So we're going to say, how many valence electrons of carbon do we have? It's 4, right? Subtract how many number of bonds do we have of carbon? It's 1, 2, 3, 4. It's 4. Plus dots. Do we have dots? No, it's 0. Therefore, it's going to be 4 minus 4, which is 0, just like what you see over here. Okay? Now, let's talk about the nitrogen. So now let's talk about the formal charge on nitrogen. The formal charge on nitrogen, this is nitrogen. How many valence electrons of nitrogen do we have? You go on your periodic table. Nitrogen, it is in group number 5. Yes, you are right. So it's 5 over here, right? And how many bonds are there for nitrogen? It's 1, 2, 3, 4. We have 4. So subtract into 4. And therefore, how many dots are there on nitrogen? 0. We don't have any dots. So we have 0 over here. You see? Now, what is 5 minus 4? 4 plus 0, it's definitely 4. 5 minus, which is this, you're going to get a positive 1 over here. Can you see that? Right. Now let's move to oxygen, the formal charge of oxygen, okay, in this molecule. So now the formal charge of oxygen, oxygen from the periodic table, it is in group number, yes, 6. That means the valence electron for oxygen is going to be 6, okay? Subtract the bonds. How many bonds are there for oxygen? We have only one. Oxygen is bonded to nitrogen, meaning it's going to be 1 plus how many electrons are there? It's 2, 4, 6. Number of electrons, not pairs. Number of electrons. Number of dots. There are 1, 2, 3, 4, 5, 6. So you can say 2, 4, 6. It's 6. And therefore 1 plus 6 is going to be 7. 6 minus 7, which is this over here, you're going to get negative 1. Okay? So these are 2 things that you need to consider when drawing a Lewis structure of these compounds. Okay? All right. I hope that was making sense. Let me erase everything over here. I hope that was making sense.